10 Most Bizarre Cosmic Phenomena. Hello everyone and welcome to my channel. In that unfathomable space, there are some phenomena so bizarre that even the best scientists have to marvel at them. It is as if there is an invisible hand in this boundless cosmic arena, manipulating the extreme mysteries of light and darkness, life and death. In this variety of strange phenomena, some can be explained, some people still half understand, some simply cannot be explained. Next, we will bring you together to explore the 10 most bizarre phenomena in the universe. 1. The Boltzmann brain. Imagine, somewhere in the infinite universe, a cloud of randomly rising and falling particles suddenly arranges itself in a strange way to form a brain. This brain is not just some kind of mysterious substance, but it has a complete sense of self, and may even have memories and thoughts similar to ours. What's even more incredible is that its existence was completely accidental, perhaps lasting only a moment before dissipating into the nothingness of the universe. If you think this scenario sounds like the plot of a sci-fi movie, it is sci-fi, but it's not just sci-fi. This is the concept at the heart of the Boltzmann brain, a thought experiment that is both creepy and fascinating. Let's go back to the late 19th century. Ludwig Boltzmann, the brilliant Austrian physicist, laid the foundations for statistical mechanics and thermodynamics. Much of Boltzmann's work centered around entropy. In simple terms, entropy is the degree of chaos. According to the second law of thermodynamics, entropy always tends to increase, which means that the universe will become more and more disordered. But Boltzmann argued that in a large enough system, even if the overall entropy is increasing, there may be some localized low-entropy ups and downs. The particles in these small regions may temporarily arrange themselves out of chaos into an orderly state. This theory explains why we see complex structures like galaxies, planets, and life, even though they seem to contradict the trend of increasing entropy. However, Boltzmann's theory leads to a surprising corollary. If complex structures can appear briefly in the random ebb and flow of the universe, why is it not possible that a brain could be born in an arrangement of random particles? Such a brain would be a product of entropy, and its formation would be extremely unlikely, but not impossible, on an infinite timescale. The concept may sound absurd, but the philosophical and scientific challenges it poses are enormous. Suppose that Boltzmann brains do exist, and that the probability of their creation is higher than the probability of the formation of a complete universe. Is it possible, then, that we are in fact Boltzmann brains? In other words, is it possible that all our memories, experiences, and perceptions are just momentary fantasies, rather than a real world that has evolved over a long history? This idea subverts our sense of reality. After all, science is based on observation and experience. If we can't be sure that our perceptions are real, but merely the product of some random ups and downs, then the very foundations of science may be shaken. Let's explore probability. Why is the creation of a Boltzmann brain more likely than a complete universe? The reason is complexity. It takes far more particle arrangements to build an entire universe than it does to build an isolated brain. Therefore, from a statistical point of view, the birth of a Boltzmann brain is easier than a complete universe. However, this does not mean that Boltzmann brains are everywhere. The probability of it appearing in even the simplest conscious system is extremely small. As you can imagine, it's as difficult as picking a particular grain of sand out of a pile. Except that in infinite time and space, anything can happen once. The concept of the Boltzmann brain has been widely discussed and debated in the scientific community. Some scientists believe that this thought experiment exposes flaws in certain cosmological theories. For example, if a theory predicts that the probability of a Boltzmann brain forming is much higher than the probability of its existence for an ordinary observer, then this may indicate a problem with the theory. This has been explored in depth by the famous physicist Sean Carroll. He points out that this probability paradox forces us to re-examine current cosmological models, especially the multiverse theory. After all, in a universe of infinite time and infinite space, almost anything is possible, but that doesn't mean we should take these extremes as reality. The concept of the Boltzmann brain lends itself well to works of science fiction, even though it may not appear directly by that name. For example, in the movie The Matrix, the protagonist's consciousness is trapped in a virtual reality, a setting reminiscent of the Boltzmann brain. If our consciousness is the product of random ups and downs, what's the difference between it and a procedurally generated virtual world? Another example is Philip K. Dick's novel Ubik. In the book, the character's reality gradually collapses and they begin to wonder if their existence is real. This storyline has many resonances with the philosophical core of the Boltzmann brain. Even though the probability of a Boltzmann brain is very low, it still serves as a reminder that the universe is more mysterious than we can imagine. Such thought experiments make us rethink the nature of consciousness, the definition of reality, and the ultimate rules of the universe. Perhaps, somewhere far away, there really is a Boltzmann brain thinking about its own existence, and we are part of its dream. 2. Galaxy jets. Galaxy jets, as the name suggests, are high-speed streams of particles ejected from the cores of galaxies. These jets sometimes stretch for millions of light-years, almost halfway across the distance of a cluster of galaxies. Imagine a cosmic laser of immense energy erupting from the center of a galaxy and sweeping across the starry sky. The sheer size and energy of these jets really makes you wonder, what is the universe up to? Let's start at the beginning. The star of all this is the supermassive black hole at the center of the galaxy. Did you know that? At the heart of most galaxies, there's one of these silent and voracious guys. At the center of our Milky Way galaxy, for example, is a black hole called Sagittarius A*, with a mass equal to 4 million suns. However, galactic jets only occur in active galactic nuclei, when the black hole is busy eating up the surrounding material. When a black hole accretes matter, a bright accretion disk forms around it. The matter in these disks spins around the black hole at high speeds and can reach temperatures of millions of degrees, emitting extremely bright light. Speaking of which, you may be thinking, no, isn't it true that black holes can't even run out of light? Yes, it is true that the light inside the black hole cannot escape, but the accretion disk is outside the black hole, so we can see these glowing substances. Then something magical happens. Instead of falling directly into the black hole, some of the matter is accelerated to near the speed of light and ejected along the black hole's powerful magnetic field lines. This creates galactic jets. Most of these jets are made up of charged particles, such as electrons and protons, which travel at speeds close to the speed of light and at ridiculously high energies. In other words, a black hole is not just a devourer, it is also a cosmic fountain. How far can these jets go, you may wonder? Scientists have observed that some jets can extend tens or even hundreds of millions of light years. For example, the jet of the famous radio galaxy Virgo A is 5 million light-years long. Compared to our Milky Way, which is only 100,000 light-years across, this is a cosmic spectacle. Then there's 3C273, the first quasar to be recognized, about 2.4 billion light-years from Earth. Its jet is so bright that it can be seen by ordinary optical telescopes. Speaking of which, an anecdote must be mentioned. In the 1980s, when scientists first observed these jets with radio telescopes, everyone was simply blown away. How could there be such huge amounts of energy flowing between galaxies? Then came more advanced technologies, such as the Hubble telescope and the Chandra X-ray telescope, which gave us a much clearer picture of the jets. The direction of the jets is also quite intriguing. They usually appear in pairs, with one beam facing up and one beam facing down, like galaxies pointing with two giant fingers deep into the universe. And they come in a variety of colors, some particularly bright in the radio band, others glowing in X-rays. These different properties reflect the interaction between the energy of the particles in the jets and their surroundings. In addition to being visually stunning, galactic jets play an important role in the cosmic ecosystem. The energy and material from the jets affect the gas clouds around galaxies, sometimes inhibiting star formation and sometimes triggering the birth of new stars. Scientists have used supercomputers to simulate these processes and have found that jets are like gardeners in the universe, shaping the future of galaxies in their own way. Another interesting finding of the recent research is that the particles in the jets can be accelerated to very high energies, even stronger than the most powerful particle gas pedals on Earth. This leads to the mystery of high-energy cosmic rays. It has been suggested that these galactic jets may be a significant source of cosmic rays. Imagine a particle from hundreds of millions of light-years away, making a long journey to finally reach Earth and hit our detectors. What a romantic and mysterious story behind it. In fact, what we know about galactic jets is still just the tip of the iceberg. For example, how are the jets precisely aligned in the right direction? Why are some jets particularly strong and others weak? These are all questions that scientists need to continue to explore. In short, galactic jets are like a visual and scientific feast from the universe. From the black holes of distant galaxies to the points of light caught in radio telescopes, it all adds up to an awe-inspiring experience of what a mysterious and magnificent place the universe is. 3. Galaxy fusion. Have you ever imagined that in the depths of the endless universe, two massive galaxies are slowly approaching each other, pulling each other, and eventually intertwining and merging into a brand new galaxy? Galaxy fusion, this cosmic dance, is one of the most spectacular and mysterious cosmic phenomena. On timescales of billions of years, galaxies do not stand still. They move slowly with the pull of gravity in the cosmic mesh. And when two galaxies get close enough to each other, gravity pulls them towards each other. This process is not a fleeting moment, but a magnificent collision that lasts hundreds of millions of years or more. Take the Milky Way and the Andromeda Galaxy, for example. Andromeda is our nearest spiral galaxy, located about 2.5 million light-years away. Astronomers predict that in about 4 billion years, Andromeda will merge with the Milky Way in a spectacular collision. This is not a catastrophic destruction, but a remodeling. The distances between the stars are extremely large, so the stars themselves rarely actually collide during the fusion. So what really happens when galaxies fuse? The first thing that happens is that gravitational interactions break up the original structure of the galaxy. Stars and interstellar material are pulled out in long tidal tails, forming arcs as brilliant as the Milky Way. Next, the galactic cores may merge, and supermassive black holes may come closer together and eventually merge into a larger black hole. A famous example is astronomy's most iconic antennae galaxies, two colliding spiral galaxies. Images taken by the Hubble telescope show them being pulled out of their magnificent tidal tails, accompanied by intense star formation activity. This phenomenon is known as a starburst, because gravitational interactions compress large amounts of gas, triggering the birth of new stars. Galaxy fusion not only changes the morphology of galaxies, but also profoundly affects their evolution. Many elliptical galaxies are thought to have formed from the fusion of spiral galaxies. Fused galaxies often lose their original spiral arm structure and become more rounded and chaotic in form. Interestingly, galaxy fusion is also an important tool for studying dark matter. In the famous Bullet Cluster, scientists have observed the collision of two clusters of galaxies. Strangely, the stars and the dark matter separated. The stars continued to move forward, but the dark matter, which does not interact strongly with ordinary matter, was thrown into a different position. This is strong evidence for the existence of dark matter. Galaxy fusion is not a rare event in the universe. In fact, it is one of the constants in the evolution of the universe. From distant quasars to local clusters of galaxies, fusions have shaped the universe as it is today. Each fusion is a reorganization of matter and the beginning of new life. The study of galaxy fusion continues. By observing fused galaxies at different stages, astronomers are able to reconstruct the history of galaxy formation and evolution in the universe. And with the commissioning of a new generation of telescopes such as the James Webb Space Telescope, we may be able to gain a deeper understanding of these dances in the universe and explore the deepest mysteries of the universe. 4. The structure of the cosmic bubble. Imagine that you are in an infinite world of soap bubble bubbles, each of which is immense and almost empty on the inside, while the bubble's membrane is densely populated with galaxies, star clusters, and dark matter. This is not the setting of some fantasy novel, but some kind of macroscopic structure of the real universe, the cosmic bubble structure. Let's start with an interesting discovery. In 1989, an observation called the CFA Redshift Survey revealed an astonishing large-scale structure in the universe. Galaxies are not randomly distributed, but form a kind of giant bubble-like network. These bubbles are almost empty, and the galaxies are densely packed like spots on a bubble membrane. Scientists have compared this phenomenon to a cosmic bubble or cosmic web. The boundaries of the bubbles are called Great Walls, such as the famous Sloan Great Wall, which spans hundreds of millions of light-years and is one of the largest known structures in the universe. So how do these bubbles form? It goes back to the very first moments after the Big Bang. Early in the life of the universe, quantum fluctuations triggered inhomogeneities in the density of matter. These inhomogeneities gradually amplified, creating the initial map of matter distribution. Gravitational forces caused the denser regions to attract more matter, eventually forming the galaxies and clusters of galaxies we see today. The interior of the bubble may look empty, but it is actually full of dark matter and thin gas. The dense regions of galaxy clusters at the bubble's borders are where gravity keeps gathering matter. How can scientists study these cosmic bubbles? One key tool is redshift observations. By measuring how much light is redshifted by the expansion of the universe, astronomers are able to determine the distance and three-dimensional distribution of galaxies. Projects like the Sloan Digital Sky Survey, SDSS, map the positions of millions of galaxies, revealing details of the structure of the cosmic bubble. What is even more amazing is that such bubble structures may not only exist in our observable universe. In some cosmological theories, the universe itself is a multiverse bubble, made up of countless bubble universes. Each bubble represents a separate universe with different physical constants and laws. The structure of the cosmic bubbles gives us a more dynamic and complex picture of the universe. This is not only a scientific discovery, but also inspires endless philosophical thinking. If we live in a bubble universe, what about outside the bubble? Perhaps, one day we will find the answer, but for now, this bubble-filled universe is fascinating enough. 5. The accretion disk of a supermassive black hole. In the depths of the universe, there is a radiant spinning disk that looks like the brightest jewel in the center of the galaxy. This is not a sci-fi scenario, but the accretion disk of a supermassive black hole, a cosmic wonder that is both mysterious and shocking. Let's start with the most basic concept. Black holes, regions of extreme curvature in spacetime where not even light can escape its gravitational pull. But you may wonder why you can see light around it if you can't even escape it. That's thanks to the accretion disk. The accretion disk, as the name suggests, is a circle of superhot plasma disk rotating around the black hole. It is made up of gas and dust that is captured by the strong gravitational pull of the black hole. When this material is attracted to the black hole and begins to fall in a spiral orbit, the intense friction and compression produces extremely high temperatures that can reach millions of degrees. This extreme heat causes the accretion disk to emit extremely bright electromagnetic radiation, including X-rays and gamma rays. One of the most famous examples is the supermassive black hole M87* at the center of the Virgo cluster of galaxies. In 2019, the Event Horizon Telescope (EHT) team published the first picture of a black hole in human history, showing the glowing accretion disk around M87 star. This groundbreaking observation provided scientists with direct evidence that black holes exist. The accretion disk is not static, but is full of dynamics and change. You can think of it as a chaotic and fiery vortex. The matter in it spirals inward, eventually crossing the black hole's event horizon, the so-called no-return zone. But the amazing thing is that some accretion disks produce jets. These jets are extremely high-speed beams of plasma that are ejected from the poles of the accretion disk at speeds close to the speed of light. Scientists speculate that the jets may be related to the action of magnetic fields. When magnetic lines of force are pulled and entangled, they can create a powerful electromagnetic force that ejects matter in the direction of the magnetic field. Let's dig a little deeper. The structure of an accretion disk is also extremely complex. According to scientific models, it is usually divided into an inner disk and an outer disk. The inner disk is extremely hot and emits X-rays, while the outer disk is cooler and is dominated by visible and ultraviolet light. Scientists observe these disks using telescopes of different wavelengths, such as the Chandra X-ray telescope and the Hubble Space Telescope. The accretion disks of supermassive black holes are not only the object of scientific study, but they are also closely related to the evolution of the universe. For example, quasars, thought to be active galactic nuclei in the early universe, are essentially extremely bright manifestations of the accretion disk of a supermassive black hole. Quasars can be brighter than entire galaxies, thanks to the enormous amount of energy released by the accretion disk. There are still many unanswered questions about supermassive black hole accretion disks. For example, why does the material in the accretion disk fall at a particular speed? What is the exact mechanism of jet formation? Even some theories suggest that accretion disks may generate gravitational waves or extreme magnetic storms, all of which are still at the forefront of scientists' explorations. In any case, the supermassive black hole accretion disk has become a mysterious door in the exploration of the universe. It not only demonstrates the most extreme physical environments in a universe, but may also be an important clue to unlocking fundamental physical principles such as gravity, magnetic fields, and the speed limit of light. 6. Ultradense white dwarfs. Imagine a star that burns out its entire life and collapses into an incredibly small object, but instead of turning into a black hole or a neutron star, it stays in a sort of intermediate state. This is the superdense white dwarf, an amazing cosmic phenomenon. This object is like a miracle of the universe, or the last struggle of a star. To understand how amazing it is, we have to start with the story of the white dwarf. Stars are like giant nuclear reactors that release energy by converting hydrogen into helium. This energy creates a radiation pressure that works against the star's own gravity to maintain its stability. However, When the nuclear fuel runs out, this balance is upset. If the star is not too massive, as in the case of a star like the Sun, it does not collapse into a black hole, but undergoes a cosmic metamorphosis. First it expands into a red giant, and then its outer shell is ejected, leaving behind a small, hot, dense core, the white dwarf. An average white dwarf star is about the size of the Earth, but has a mass close to that of the Sun. That means it's unimaginably dense. A single teaspoon of white dwarf material may weigh more than a few tons. However, some white dwarfs are not ordinary. They are much denser, even approaching the limit of collapsing into neutron stars. Why is that? The key is mass. If a white dwarf's mass approaches the Chandrasekhar limit, about 1.4 times the mass of the Sun, its fate becomes very complicated. The Chandrasekhar limit was proposed by Indian physicist Subramanian Chandrasekhar. He found that the simple merger electron pressure, an anti-gravitational mechanism provided by quantum mechanics, within a white dwarf can only support up to a certain level of mass. Once this limit is exceeded, the white dwarf collapses into a neutron star or even a black hole. But there are some white dwarfs that are close to this limit, but by some coincidence maintain their equilibrium. The matter in these superdense white dwarfs is compressed even more tightly, making them among the densest non-black hole objects in the universe. The density of superdense white dwarfs is truly breathtaking. A cubic centimeter of matter can weigh hundreds of tons. What kind of concept is that? Imagine compressing the entire Mount Everest to the size of a dice, which is barely close to their density. This extreme density leads to strange gravitational phenomena. For example, if you were to stand on the surface of an ultradense white dwarf, which is impossible, you would find yourself gravitationally pulled as thin as a piece of paper, because the surface gravity could be billions of times that of the Earth. The discovery of superdense white dwarfs is a miracle in itself. For years, astronomers have been looking at white dwarfs in the Milky Way, trying to understand their mass distribution. Until recently, high-precision astronomical instruments, such as the Hubble Space Telescope, have captured several exceptional white dwarfs whose spectral properties show extremely high masses and densities. One example is the discovery by astronomers of ZTF-J 1901+1458, a white dwarf star with a mass close to the Chandrasekhar limit, a fraction of the diameter of the Earth, but with 1.3 times the mass of the Sun. This object is of great interest to the scientific community because it is just one step away from collapsing into a neutron star. An interesting question is why these superdense white dwarfs have not collapsed into neutron stars. The answer may have to do with their formation process. Some white dwarfs may have formed from the merger of two white dwarfs in a binary star system. When two white dwarfs orbit each other, grow closer and eventually merge, their masses superimpose. If the total mass of the merger approaches, but does not exceed, the Chandrasekhar limit, a superdense white dwarf is formed. Although superdense white dwarfs can maintain themselves for a while, their ultimate fate is to collapse into a neutron star or undergo a violent supernova outburst. Once collapsed, these objects move on to the next stage of the universe, either becoming silent neutron stars or ending their lives with a spectacular explosion. Ultra-dense white dwarfs are not only a hot topic in astronomical research, but also provide valuable data for understanding the behavior of matter under extreme physical conditions. Their existence allows scientists to delve deeper into the interplay of gravity, quantum mechanics, and nuclear physics. As one astronomer once said, these objects are like laboratories of the universe, where matter is compressed to its limits and we are able to glimpse the deepest physical laws of nature. Interestingly, ultra-dense white dwarfs have also inspired a lot of philosophical thinking. Imagine these objects were the end of a star's illustrious life, but instead of completely letting go, they hold on in a unique way, becoming extremely rare in the universe. They seem to be telling us in their own way that no matter what kind of pressure they face, as long as they find their own balance, they can create extraordinary life forms. Perhaps this is also a lesson we can learn from the universe. 7. Binary star system. When it comes to strange phenomena in the universe, binary star systems are definitely one of the most fascinating. Imagine two stars orbiting each other in the night sky, interdependent, like a pair of eternal dance partners. The sight is both romantic and mysterious, but the science behind it is equally amazing. A binary star system, as the name suggests, is a system of two stars that orbit each other because of their gravitational pull. This phenomenon is actually quite common in the universe. In fact, according to astronomers, about half or more of the stars in the Milky Way are part of a binary or multiple star system, rather than living alone like our Sun. Interestingly, the discovery of binary star systems is not so intuitive. Until one looks at the night sky through a telescope, it is difficult to realize that a bright, seemingly ordinary star may actually be two or more stars in close proximity. For example, the famous Betelgeuse, the fourth star in the constellation Orion, initially appears to be a red giant, but further observations show that it is actually a multiple star system. Binary star systems are categorized into many types, depending on the spacing and orbits of the stars. The most common are the following categories. 1. Separate binaries. Two stars are far apart, each retaining its own outer atmosphere, hardly interfering with each other, and only being pulled by each other's gravity. 2. Semi-separate binaries. One of the stars is expanding in size and starting to spill material into the companion star, forming what is known as a lossy flap overflow. 3. Close binary. The stars are so close that they may share each other's material, even forming a common envelope. How do binary star systems like this form, you may ask? Scientists believe that most binary star systems form during the early stages of star formation. When a nebula of gas and dust collapses to form a star, the primordial rotation may cause the disk of gas to split into two parts, each forming a star. Another possible scenario is that after a star forms, gravity attracts nearby material, eventually forming a companion star. Binary star systems are not only beautiful, but they are also important in astronomical research. For example, by studying binary star systems, we can more accurately measure the mass of a star. The classic example is the eclipsing binary, which astronomers use to determine the size and mass of a star. An eclipsing binary is a system in which two stars orbit each other in a plane that is exactly aligned with our line of sight, so that we can see that they alternately block each other's light, creating periodic variations in brightness. A famous astronomer, Eddington, once said, "The mass of the star is the key to astronomy." In eclipsing binary systems, scientists can accurately calculate the mass and orbital parameters of the star by observing the light variation curve as well as the Doppler effect. This method has even helped scientists discover many unseen companion stars, such as white dwarfs, neutron stars, and even black holes. Binary star systems also harbor some amazing phenomena, such as X-ray binaries. In these types of systems, there is usually a dense object, such as a neutron star or black hole, to which its companion star is constantly transferring material, forming an accretion disk. When this material is heated to extremely high temperatures, it emits intense X-rays. These vampire stars of the universe provide a natural laboratory for scientists to study extreme physical conditions. There is also an amazing binary star system known as a pulsar binary. A pulsar is a neutron star that rotates at high speeds and emits periodic electromagnetic pulses. The first pulsar binary was discovered in 1974 by astronomers Russell Hulse and Joseph Taylor, which led to the proof of the existence of gravitational waves in general relativity. This discovery culminated in the direct detection of gravitational waves by the LIGO experiment in 2015, setting off an astronomical revolution. Sometimes binary star systems can produce even more spectacular phenomena, such as supernova explosions. In a class of events called Type Ia supernovae, a white dwarf star accretes material from a companion star and exceeds the famous Chandrasekhar limit, about 1.4 times the mass of the Sun, triggering a violent thermonuclear explosion. The brightness of such supernova explosions is so stable that they are used as standard candles in cosmology to help measure the rate of expansion of the universe. Of course, the study of binary star systems is still full of unanswered questions. Scientists are still exploring their formation processes, evolutionary paths, and ultimate fates. Some binaries may eventually merge into one massive star, while others may co-evolve into a pair of white dwarfs or even trigger more violent events, such as gamma-ray bursts. Have you ever imagined what it would be like if our Sun had a companion star? Some scientists have even proposed the Nemesis hypothesis, which states that the Sun once had a dim companion star that may have triggered the mass extinction of life on Earth in ancient times. However, this hypothesis has not yet been proven. Binary star systems are like those mysterious duo dancers in a universe, both gentle and full of power. They make our understanding of a universe deeper, and make us realize that in the vast sea of stars, behind each star there is an amazing story. 8. Gravitational waves. Have you ever thought that those mysterious fluctuations in the universe that you can't see or feel really exist? Gravitational waves are one such marvelous existence. Imagine if space-time was a giant rubber cloth, then when an object with a lot of mass, such as a star or a black hole, is placed on top of it, it bends the cloth. When these objects move, especially if they collide or merge violently, it's like dropping a rock on the rubber cloth, and those ripples spread throughout the universe. These ripples are gravitational waves, a perturbation of space-time that travels at the speed of light. The concept of gravitational waves was first proposed by Albert Einstein in 1916 as part of his theory of general relativity. Einstein thought at the time that gravitational waves might be too weak for humans to ever detect them. But who would have thought that 100 years later, this seemingly far-fetched idea would actually become a reality? On September 14, 2015, scientists finally made the first direct detection of gravitational waves. The detection came from the merger of two black holes, 29 and 36 solar masses respectively, which collided about 1.3 billion light-years away from Earth, releasing gravitational waves that traveled across the universe and were captured by LIGO, Laser Interferometric Gravitational Wave Observatory. The discovery rocked the entire scientific community and left no doubt that the 2017 Nobel Prize in Physics would be awarded to the three core scientists of LIGO. How LIGO works is actually very interesting. It consists of two huge L-shaped devices with each arm up to 4 kilometers long. Laser beams are reflected back and forth through these two arms, measuring small changes in space through the principle of interference. When a gravitational wave passes through, it causes tiny stretches and compressions in spacetime, causing extremely small changes in light travel that are as small as the diameter of an atomic nucleus. Gravitational waves not only validate Einstein's theory, but also open a whole new window of astronomical observation. Previous astronomical research relied on optical telescopes, electromagnetic waves, and other means of observation, but gravitational waves allow us to hear the violent events in the universe, as if to give us an ear that can feel the vibration of the universe. Interestingly, gravitational waves have also helped scientists identify neutron star mergers. In 2017, LIGO and Europe's Virgo gravitational wave detector together detected a gravitational wave signal from a neutron star collision. What made this event special was that it was accompanied by a simultaneous burst of electromagnetic waves, bringing together more than 70 telescopes from around the world to participate in the observation. This not only verified the existence of gravitational waves, but also helped scientists further understand the origin of heavy elements such as gold and platinum. Gravitational wave research is not only a scientific breakthrough, it is also filled with a spirit of perseverance and exploration of mankind. The original idea of LIGO was proposed in the 1970s, but it was not officially built until the beginning of the 21st century, and underwent many upgrades and improvements before the great discoveries that followed were made. Today, scientists continue to improve gravitational wave detectors, such as the soon-to-be-built LISA, Laser Interferometric Space Antenna, which will be deployed in space to detect gravitational wave signals at even lower frequencies. These detectors have the potential to help us directly observe cosmic primordial gravitational waves after the Big Bang, revealing the very first moments of the universe's birth. The discovery of gravitational waves makes us realize that the universe is not only a stage for light and matter, but also a constantly trembling tapestry of space and time, where every vibration may come from the depths of the distant universe, telling of an amazing cosmic event. 9. Neutrino-Explosion. Have you ever heard of a mysterious particle called neutrino? They are one of the most elusive beings in the universe, barely interacting with other matter, like ghost particles. But when a violent event occurs in the universe, such as the explosion of a massive star into a supernova, neutrinos emerge in swarms, forming what is known as a neutrino explosion. This is not only an orgy of particles, but also an important clue to understanding the mysteries of the universe. Let's start with a real event. On February 23, 1987, the astronomical world experienced a historic moment. On February 23, 1987, the astronomical community experienced a historic moment when the Kamioka probe in Japan and the IMB probe in the United States detected a neutrino burst from the Large Magellanic Nebula, LMN, at almost the same time. The outburst came from supernova SN 1987A, a violent explosion at the end of the life of a star about 160,000 light-years away. Amazingly, these neutrino signals reached Earth before visible light signals did. Why is that? This is because neutrinos barely interact with matter and are able to escape the moment the star explodes. Light, on the other hand, needs to pass through the dense plasma inside the star, delaying it some time before it breaks through the barriers to reach Earth. Neutrino bursts are not only an amazing natural phenomenon, they also provide scientists with valuable research tools. First, they help us understand the internal mechanisms of supernova explosions. Scientists believe that during the core collapse of a supernova explosion, The matter is so dense that a large number of neutrinos are created and released there. The energy of these neutrinos even exceeds the energy released by visible light explosions. Neutrino bursts are extremely difficult to detect. Because neutrinos are extremely difficult to interact with matter, scientists need to build extremely sensitive detectors, such as the famous Candy, a huge underground detector filled with 50,000 tons of ultrapure water, located deep in the mountains of Japan. The detector records neutrino footprints by capturing the faint Cherenkov radiation produced when a very few neutrinos collide with the nuclei of atoms in water molecules. Scientists are also using neutrino bursts to study the most extreme phenomena in the universe, such as gamma-ray bursts, GRBs. These brief but extremely bright cosmic events may also be accompanied by the production of large numbers of neutrinos. By combining observations from neutrino detectors and gamma-ray telescopes, scientists hope to unravel the causes of these extreme astrophysical events. Neutrino bursts may even reveal the hidden dark matter secrets of the universe. Some theories suggest that dark matter particles may produce neutrinos under extreme conditions. Detecting the nature and number of neutrinos could help to validate these cutting-edge theories. Interestingly, the neutrino explosion is also closely related to the history of human exploration of the Sun. In the 1960s, scientist Raymond Davis Jr. conducted an experiment to detect solar neutrinos at the Deep Underground Laboratory in the United States. He captured some neutrino signals in a huge pool of chlorine solution, but far fewer than expected. This solar neutrino problem plagued the scientific community for decades until the 2001 discovery by the SNO, Sudbury Neutrino Observatory detector that neutrinos oscillate as they travel through space, i.e., they oscillate between the three different types, electron, muon and muon of neutrinos. Three different types, electrons, muons and tau-s, as they traveled through space, thus solving the puzzle. Neutrino eruptions remain a mysterious area of research. Scientists continue to build more sensitive detectors around the globe, such as the Candy in Japan and the Dune detector in the United States. These devices will help us capture more neutrinos from supernovae and even detect the neutrino background radiation left over from the Big Bang in the early universe. Neutrino outbursts are like whispering signals from the universe to us, which, though faint, contain the deepest secrets of the universe. Perhaps in the not-too-distant future, we will be able to unravel the ultimate mystery of the birth and evolution of the universe through the messages of these ghostly particles. Physicist John Bockall once said, "Neutrinos are messengers through the universe, and they carry messages from the deepest recesses of the universe." 10. White holes. Have you ever heard of a white hole? Doesn't the name immediately remind you of a black hole? Yes, white holes are the mysterious opposite of black holes. Instead of swallowing everything, white holes repel everything. If a black hole is like a bottomless pit, a white hole is the fountain of the universe. All matter and energy is discharged, refusing to let anything come near. The story behind this is even more amazing than it seems. The concept of a white hole was originally extrapolated from Einstein's theory of general relativity. Simply put, the theory of general relativity describes the curvature of spacetime, and black holes are the extreme manifestation of this curvature. Black holes have an event horizon, which means that once this boundary is crossed, no light can escape. Scientists wondered, if spacetime can bend extremely in one direction to form a black hole, can it bend in the other direction to form the exact opposite structure? Thus, the theory of the white hole was put forward. It is a time reversal region, from which all the matter can only spurt out, and can never go in. Imagine, if a black hole is the entrance to spacetime, a white hole could be its exit. Some have even speculated that black holes and white holes might be connected by some kind of wormhole. You fall through a black hole and end up being ejected through a white hole in another place. The behavior of white holes is very special. A black hole is a predator, devouring all approaching matter, while a white hole is a denier, bouncing off anything that tries to get close. Imagine a fountain that keeps shooting jets of water outward, but you can never get to it against the current. Interestingly, general relativity allows for the existence of white holes, but their physical significance is baffling. Scientists imagine that if white holes existed, they would have disappeared long after the Big Bang. Because these all-excluding objects are so unstable in the universe, they could disintegrate at the slightest perturbation. At this point, some people may ask, since a white hole repels everything, where does the stuff it spews out go? That's what's fascinating about a white hole. It may have something to do with the birth of the universe. Some scientists speculate that the Big Bang itself may have been a white hole event. The Big Bang is characterized by the release of large amounts of matter and energy in a very short period of time, and this behavior is very similar to the spewing of white holes. Some have even suggested that our universe may have been born from a giant white hole. Although the white hole theory is interesting, scientists have yet to find any direct evidence of its existence. However, that hasn't stopped people from imagining it. For example, there was a gamma-ray burst known as GRB 060614 that at one time led to suspicions that it might be related to a white hole. The burst lasted 102 seconds and released a huge amount of energy without any sign of a black hole. There was speculation that it could be a sign of white hole activity, but this idea was quickly dismissed, and more evidence suggests that it could be some other astronomical phenomenon, such as a star merger. White holes may still be just a theory in the scientific community, but they have long been a source of inspiration in science fiction. Star Trek: The Next Generation has made references to white holes. In the show, white holes are a source of extreme energy. Other novels describe white holes as the exit from the universe, or even the starting point for time travel. Imagine if white holes existed. Could we use them to explore the other side of the universe? Or would it be the entrance to the multiverse? These questions remain unanswered for now, but they certainly ignite our curiosity. Although white holes are still theoretical, their existence is a reminder that there are still too many unanswered questions in the universe waiting to be solved. From black holes to white holes, this marvelous dichotomy makes us rethink the possibilities of space and time. Well, that's it for this installment. Likes and comments are welcome. Thanks for watching.